All right, so continuing with these notes, we just saw this particular formula that essentially explains how exponentials feel related to this polar form of complex numbers. That this thing we had with CIS theta, right, cosine theta plus I sine theta, that's basically the same as e to the I theta, right? This is what it means to take imaginary exponents. It somehow is linked to complex numbers in polar form. And of particular note is the example where we plug in pi. So by this formula, e to the I pi would be cosine of pi plus I times sine of pi. Cosine of pi is -1. Sine pi is 0. So we have this formula here. That's e to the I pi is -1. Right? And let's just pause here. Ordinarily, when we take e and raise it to a power, right, something you've learned before here is that the range is all positive numbers. If we take a real number exponent for e, our answer will be a positive real number. Here, we're taking an imaginary power, and we're getting an answer that doesn't feel like the kind of answer we got before. When we restrict ourselves to real numbers, the output of e to a power is always positive. Here, it's negative. Right? I could, in fact, make it non-real if I cooked up something a little more unusual. So we're just noticing that once we open up to the realm of complex numbers, our notions about domain and range start to change. And some people like to rewrite this in this form, where they add 1 to each side. This version unifies what are arguably 5 of the most important numbers, if not the 5 most important numbers, in one single equation, right? E is certainly very important. The imaginary unit I is certainly very important. Pi is very important. 1 is an extraordinarily important number. It's the multiplicative identity. And 0 is the additive identity. And I'll just point out, identities just mean they're numbers where when you do an operation, nothing changes. Right? 1 times x is always equal to x. That's only true about the number 1, and it's pretty interesting. X plus 0 is equal to x. That's only true about the number 0, and that's interesting. Right? So 1 and 0 are exceptionally interesting and important numbers, besides the fact that they're just small and easy to count with. And once we have this jumping off point, we can start talking about other operations applied in unusual situations, right? Again, we're expanding our notion of domain and range, right? Someone might look at this and say, oh, suddenly it makes sense to talk about the natural log of -1. Right? You may have learned, oh, we're not allowed to take the natural log of a negative. Well, when we open up to thinking about all complex numbers, we can take the natural log of a negative, but the answer is imaginary. Right? So we're going beyond any intuition as to what natural log is supposed to be doing. But if this has a meaning at all, this is the meaning we've inherited. Right? We could also do things like, hey, suppose I wanted to figure out cosine of I. Right? This is imaginary. We can't interpret this as an angle, but maybe by using Euler's formula up here, we can deduce what it means, or what it has to be equal to if it has a meaning at all. So here's what I'm going to do. I am going to say that, so we know e to the I pi, e to the I theta is cosine theta plus I sine theta. Right? And we're trying to figure out what cosine of I is. So everywhere I see a theta here, I'm going to put in I. So e to the I times I is cosine of I plus I times sine I. So what that means is e to the -1, I times I is -1, is cosine of I plus I sine I. Now I'm going to do the same thing with negative I. So EI to the negative I is cosine of negative I plus I sine of negative I. Here, I times negative I is negative I squared, which is 1. And now we're going to use properties we know about sine and cosine, and I'm waving my hands a little bit about why we're still allowed to do these with imaginaries. We can make sense of this by thinking about the polar form, but I am just going to remind you that cosine is an even function. Whether we plug in a positive or negative, we get the same answer, while sine is an odd function. And that extends to non-real input. So cosine of negative I is the same as cosine of I, while sine of negative I is the opposite. So now what I'm going to do is I'm going to take this equation here, and I'm going to take this equation here and copy it over. Now, what happens when we add these together? Here I will have e to the first, which is just e, plus e to the negative 1, which is 1 over e. I get 2 cosine I, and then here these cancel. So what that means is that cosine I is equal to, let me give myself a little more room, 1/2 of e plus 1 over e. We can't really make sense of that in terms of angles in the unit circle, but we've deduced that if we are going to attempt to extend functions like sine and cosine to non-real numbers, this is the value that we will get. There's another way we can get this with Taylor series, which is something we'll be looking at down the road. And I want you to just look at this, right? And maybe even pull out a calculator. Right? Look at that value, 1/2 e plus 1 over e. So first of all, we'll note that's a real number. There are no i's on the right side of that equation, so we are getting a number in the usual sense. But what's interesting is that this number is bigger than 1. Right? E is about 2.7, its reciprocal is about 0.4. Right? This comes in around 1.5, but it's bigger than 1. So this is interesting because something that you've learned before is that, oh, the range of cosine is always between -1 and 1. That's only true when we're taking cosine of a real number. As seen before, once we start extending, we will get unusual answers in terms of domains and ranges. If we try to take cosine of an imaginary number like I, in this case, we are getting a real number as our answer, but it's bigger than 1. Right? It feels like it's a forbidden value for cosine because we're totally extending this cosine function. Right? All kinds of things like this can be done with complex numbers. Pretty much all of the arithmetic and algebra and calculus that is developed for real numbers can be kind of translated over into complex numbers. And we lose a lot of intuition about what these things are supposed to mean. But if you carefully just kind of go through computations like this, you're able to deduce a lot of values. Okay, that is it for this video.